Today we're starting on section 5.3, and if the last class is any indication, I am not going to finish. So I guess I better start hustling through it. Okay, so in the last two classes, we were discussing 5.2. 5.2 was on definite integrals. We learned that the definite integral of a function gives the area underneath the curve, the signed area between the curve and the x-axis, and they were defined in terms of Riemann sums. They were defined in terms of the limit as the number of subintervals goes to infinity of the Riemann sum, which was a difficult to work with definition. Actually doing computations with it can be tedious, difficult, hard, and in fact, not generalizable. But I mentioned a few times that we're going to learn a better way. So today, I'm going to show you that better way that I've been talking about today, this lecture, and the next lecture. So that better way is going to be the content of this theorem. And this theorem is called the Evaluation Theorem. That's our textbook's name for this, by the way. As far as I know, I haven't heard that phrase used in any other textbooks. And next lecture, we're going to give this a different name. So sorry, but for today, we're calling it the Evaluation Theorem. And it says that suppose that f is a continuous function on some interval a to b, and capital F is any antiderivative of little f. Recall, antiderivative just means that capital F prime of x is equal to little f of x. Then we have the following formula for the definite integral of a. So the definite integral, this formula is for the definite integral of little f. The definite integral from a to b of f of x dx is equal to capital F at b minus capital F at a. Okay, so that's our big, amazing new formula. It's super useful. It says that the definite integral of little f, which is the signed area beneath the curve, apparently, amazingly, only depends on the values of this antiderivative function at the two endpoints. So that's kind of crazy, right there in itself. How are you encapsulating all this information about the function f and the area beneath it by just the values of some function at the two endpoints? Let me give you an example. Let's see. We know that 1/3 x cubed is an antiderivative of x squared. Hence, if we want to integrate x squared, let's say from 0 to 1, well, according to our new evaluation theorem, this is going to be 1/3 of 1 cubed minus 1/3 of 0 cubed, which is 1/3. As we know, actually, we've already seen that result before. And let's see. How about I now prove to you the evaluation theorem? Now, this is not a proofs course, okay, but I should show you some proofs, especially given that this is one of the two most important theorems that we're going to see in the whole class. So for what follows, you don't have to really worry about understanding every single step or copying it all down. I would rather that you maybe take a break from copying stuff down and just relax a bit and just watch. You're not going to have to do this yourself. The point is to just convey some of the ideas here and additionally give you some ideas about how proofs work. So here's the proof of the evaluation theorem. For starters, we have that delta x, the width of the subintervals is b minus a over n. As we know, that's a formula we've used before in the context of ring-on sums. And as usual, we can label the endpoints of the subintervals by indexing these x values. We start with x0, which is a. Then after that comes x1, which is a plus delta x, and then x2, and then x3, et cetera, all the way up until xn, which is equal to b. Now let's start manipulating the equation in the evaluation theorem. So the right side of the equation is f of b minus f of a. I can rewrite this as f of x sub n minus f of x sub 0. And in fact, let me now do a common trick in analysis proofs. I'm going to add and subtract a bunch of the same term. So I'm going to subtract f of xn minus 1, and then I'm going to add f of x sub n minus 1. You're allowed to do that because when you add and subtract the same term altogether, that's just adding 0, which gives you the same thing. So I'm going to do that for all the intermediate terms. Let's see, all the way up until minus f of x1 and plus f of x1 and minus f of x sub 0. But that can be written more succinctly in summation notation. Sum of x sub I minus f sub I minus 1. Now I'm going to employ this thing called the mean value theorem. This is something which you should have seen in 10A. If you don't remember it, that's fine. Don't worry about it. You can sort of take my word for it. But let me write down what the mean value theorem says, applied into this context. So by the mean value theorem, there exists a point which I'll call x sub I star in the ith subinterval. Such that the following holds. Such that the difference in the values of capital F at the endpoints of that interval is the derivative evaluated at this special point times the width of the subinterval. Okay, now again, if you forgot about the mean value theorem, not a big deal. You can take my word for it. Briefly, what the mean value theorem says is, if you have a function that's differentiable on some interval, then at some point in the interval, its slope was equal to its average rate of change over the interval. In sort of practical, like down-to-earth terms, this says that, let's say you drive from San Diego to Los Angeles, and your average speed for the trip was 60 miles an hour. Well, then at some point during that trip, your speedometer said 60 miles an hour. That's just the application of the mean value theorem. So applying that to what we already have, let's see, I get, I'm going to replace this term right here with what I just found it to be from the mean value theorem. And that gives me f of b minus f of a equals the sum from I equals 1 to n of f prime of x sub I star times xi minus x sub I minus 1. Oh, but capital F prime was little f. That was given in the setup. Let me just show you. Right here. Capital F prime is little f. And the difference between any two consecutive endpoints of the subintervals is what we called delta x. My point is, this could also be written as the sum from I equals 1 to n of f of x sub I star delta x, which should remind everyone of a Riemann sum. That, oops, sorry, that's sum from 1 to n. That is exactly a Riemann sum. Yeah, so if I let n go to infinity, the one side of the equation doesn't even depend on n. And that's the f of b minus f of a side. And the other side, that's the definition of the definite integral. So by definition of the definite integral, I get that, I get the definite integral from a to b of f of x dx. Okay, so that's a little proof. Any questions on that? It's in the book, by the way. And like I said, sorry?
Sorry. Do we have to know how to do this proof?
No.
Okay.
Yeah, I figured I should show you some proofs, though. It's a super important theorem. I shouldn't really just like give you your most important theorem and tell you to take my word for it when it can be proven with things that we already know. No. Like I could sit down with you for like an hour and this proof would totally make sense. It's not, doesn't use things that are that far beyond what you've already seen. So anyway, that's that. Let me now show you some examples. So let's find the area underneath y equals sine x for x between 0 and 2. And graphically, let's see. There's the graph of sine x. So There, you can more or less see the region we're interested in right there. And there's 2 right there. So let me just shade in the region. So basically, we're asking for the area of this region right here. Maybe I should call it like A for the moment. So let's see. A, the region that we're trying to find the area of, apparently is equal to the integral from 0 to 2 of sine x dx, okay? That we already know. The problem is, how do we compute that? Because it's not like A is made up of triangles or circles. Now we could try computing some Riemann sums, and that sounds horrific. I don't even want to try going down that path. Fortunately, we have a new theorem which we can apply, which says that all we need is to know what a antiderivative of sine is. So we know that negative cos x is an antiderivative of sine x. Hence, a, which is this integral right here, is equal to, well, according to our new evaluation theorem, we just need to plug in the endpoints, 0 and 2, to cosine. So that will be negative cos of 2 minus negative cos of 0. This is negative cos 2 plus 1, which I can even calculate numerically. It's about 1.4. Which looks about right if you look at the picture. Okay, any questions on that?
Professor, I have a question.
Mm-hmm.
So we know that negative cosine x is one antiderivative for sine, but let's say that the antiderivative was maybe negative cosine x plus 1, then wouldn't that like end up changing the area if we were plugging in endpoints to find?
Okay, excellent point. So yeah, Aditi pointed out an excellent point. So what if we had used negative cos, what if we had used a different antiderivative? Like negative cos x plus 1, for example.
Mm-hmm.
So if we had used negative cos x plus 1 and plugged that into the evaluation formula, let's see what would have happened. Then we would have found that the integral from 0 to 2 of sine x dx is, okay, so I'm going to plug in 2, and then I'm going to subtract the evaluation at 0, and look what happens to the plus 1s. They cancel each other out. And we just get the same answer as before. Negative cos 2 plus 1, which is cosine of 0. So that's why in the evaluation theorem, I said any antiderivative. Any antiderivative will work. We already learned previously that any 2 antiderivatives differ by a constant. But when you end up subtracting the function at one end from the value at the other, that constant just goes away.
Okay, thank you so much.
Yeah, no, yeah, excellent question. Let's see. Let me ask you all a quick yes or no question. So the area below y equals sine x on, how about 0 to pi is 2. Yes or no, folks? Everyone hit the yes or no button. Now here, I'll shade this region in with what's a good color? Ooh, how about blue? So now we're looking for this area. Well, okay, let's see what it is. It's going to be the integral from 0 to 2 of sine x dx. So that will be negative cos, sorry, not, my bad, sorry, not 0 to 2, 0 to pi, sorry about that. That will be negative cos pi minus negative cos 0. That's negative 1 minus negative 1, which is 1 plus 1, which is 2. So the answer is yes. Let me give you some new notation, which you'll like. It'll make some of this easier. So if we have some function and we want to evaluate it at one number minus the value at another number, that is to say, if you want to do, let's say, g of b minus g of a, we can abbreviate that with a vertical evaluation bar with a subscript and a superscript. Okay, so this is kind of a more convenient way to write a lot of these formulas. So for example, in the above calculation, 0 to pi sine x dx, I could also have written that as negative cos x, and then the vertical bar and the 0 and pi. Now let me ask you a related question. Let's still use sine. So, new question. Now should I call it? How about B? Now let B be the area below sine from 0 to x. So I'm letting the endpoint of the interval be a variable. That's what's new here. Let's say, I don't know, x is like right there. Then let's see if I can draw B. B will be this region here. Notice that its area depends on x. Just kind of weird. We previously tried x being pi or 2. Now let's just leave it as x, and let's see what happens. Then, as we've seen, b is the integral from, well, now it'll go from 0 to x. of sine, and I guess I shouldn't use the letter x anymore. So how about I'll use t. Let me know if anyone is unsure about this last equation that I just wrote. Because I did a couple things going on. There's a couple things going on here. I switched up my dummy variable from x to t. You can use any letter you want for your dummy variable, but I didn't want to use x because I'm using it somewhere else, namely as one of my limits of integration now. So apparently b is equal to negative cos t evaluated from 0 to x, which is negative cos x plus 1. Notice that we got an antiderivative of sine right here, and that's no accident. What I just showed you here, I'm gonna repeat again in the next lecture. So I'm kind of showing you, I'm gonna show you the same thing a couple different times. So this is just the first instance, and this motivates a new definition, okay? Previously, we would have said that negative cosine, or rather negative cosine plus 1 is an antiderivative of sine. We are now going to use a new word, but which means the same thing as an antiderivative. And the new word is indefinite integral. So here's the new definition. Let me see. Got that. So if capital F of x is an antiderivative of little f of x, i.e., capital F prime of x is equal to little f of x, then we're going to write what looks like an integral sign, except I'm not going to put any limits on it. And if capital F is any antiderivative of little f, then this integral looking thing will be equal to capital F of x plus c. And we call this the indefinite integral of f. Okay, so c, by the way, here is allowed to be any constant. You might be wondering, what's the difference between an antiderivative and an indefinite integral? And the answer is there's no difference. They are two words that mean the same thing. So your next question is, well, why do we have two words that mean the same thing? And the answer to that is the context in which they arrive. So remember, we learned antiderivatives in the context of derivatives. By definition, the antiderivative, it was like the opposite of taking a derivative. It was the thing where once you took its derivative, you got to the original function. Indefinite integrals, even though they're the same thing as antiderivatives, they arose through a different motivation. And it's what I was trying to say here when I stuck in an x as the upper limit of a definite integral. So by sticking in a variable to be the upper limit, we arose with this thing called the called the indefinite integral, which turns out to be the same thing as an antiderivative. So they end up being the same thing. The two words mean the same thing, but they kind of arose out of different motivations, if you will. One being the definition of a derivative, the other motivation being the definition of an integral. And they're connected with our new evaluation theorem. So this is probably, a bit confusing, I'm sure, especially all the plus C business, like when do you include it, when do you not? Let me just give you like a general rule. So always include plus C when calculating indefinite integrals. Yes or no? We need to include plus C for the computation of definite integrals. Yes or no, folks? Oh, good. Most of you are saying no, and that is correct. That was thanks to Aditi's question earlier, who astutely asked what happens if we used like a different antiderivative, and it ended up canceling out. So the answer is you don't need to write the plus C. If you did, you would be wasting your time because it's just going to cancel out anyway. So you should always write them with indefinite integrals, but there's no reason to write them for definite integrals. Kim, did you have a question?
Yeah, so where did you get the +1 at the top from? Because wouldn't it be like plus C instead of +1 up here?
Yes. I just chose a specific one. I could have done +10 or plus C or any other number.
Okay, thank you.
Now that we've learned the word indefinite integral, we can translate all of our statements about antiderivatives into statements about indefinite integrals. So back in week 1, I wrote down like a list of common antiderivative formulas. So I can now rewrite all of those, but in the context of indefinite integrals instead of antiderivatives, but all the formulas are going to be the same. So like, for example, let's see, we just saw that the indefinite integral of sine is negative cos. The indefinite integral of cos is, let's see, that's the antiderivative of cos, which is sine. Let's see, how about e to the x? This is going to be the antiderivative of e to the x, which is e to the x. How about, oh, here's an important one, is the power rule. So the antiderivative of x to the n is, let's see, add 1 to the power and divide by the new power. Oops. If, that is, the power is not negative 1. If the power is negative 1, then we have its own special formula involving ln. involving ln of the absolute value, which I think was probably the cause of the #1 mistake on the quiz, on quiz 2, was forgetting about the importance of the absolute value right there. What else do we have? There's okay, I guess there's secant squared. So the integral of secant squared x dx is tan x plus c, and the integral of 1 over 1 plus x squared dx is arctan x plus c. And what else do we have? Any more that I'm forgetting? Well, we've got our linearity rules. Like, again, I'm just putting down the same rules that we had for antiderivatives. So if we take the indefinite integral of a sum, then that will be the sum of the indefinite integrals. And if we multiply by a constant, say r, then we can pull the constant out in front. Okay, so let's see, did I make any typos in all that? No? Huh. Not that. Any questions on this?
Do the last two need plus C anywhere, or is it not necessary?
Good, good. I'm glad you asked. Now, the same question. Let's go look back when I first gave this table, which was back. Oh, it's right here. Yeah. So I hoped someone asked the same question back here. And okay, so here we have a plus C. That is good. On the current table, I did not write plus C, and here's why I didn't write it. I still have an antiderivative sign on the right-hand side of the equation. So both of those, say, if we're looking at this formula here, will have an arbitrary constant. So I could have written plus C, but I don't have to, because this plus C is just going to get like absorbed into the one from here or the one from here. So there's really no reason to. And same with this next equation. I could have written plus C, except we would be writing a plus C anyway when we compute this antiderivative. Like, let's see, should I do an example of this right now? Hold on, let me see how much time I have. So here's a quick example of what I'm talking about. So if we wanted, say, the antiderivative of x plus x squared dx, according to our new formulas, this would be the antiderivative of x dx plus the antiderivative of x squared dx. We can evaluate both of these. The first one is x squared over 2 plus, let's say, c1. The second one is x cubed over 3 plus c2. But one constant plus another constant is still a constant. It's still something that doesn't depend on x. So I could just as well write this as x squared over 2 plus x cubed over 3 plus, I don't know, c3. Or just c, if you will. In fact, let's just call it, how about just c? So I know it's a bit confusing, for sure it is. But once you get some practice with it, it'll make a bit more sense. But I imagine a lot of people are kind of confused about the plus c business right now. Hopefully that helps, Rita.
Yes, thank you.
Juliana, did you still have questions?
Yeah, I just wanted to recap on what you just said. So essentially, we only need to put the plus c there when we're actually evaluating for the integral.
Yes, very good. Exactly.
Okay.
Now, let's see. Let me give you a definition, which means I'm probably going to end right where I ended with my other class. Oh, and let me just point out that you can see a longer list of these formulas in the book on page 358. For a longer but similar formula list. Also, you should definitely read the examples in the book. So, I'm not going to have time to do every possible type of example in this class. So you should definitely read examples 3 through 6, for example. Yeah, so read those examples that are in the text. And the end of this section is about applications, because there are like a million great, interesting applications to integrals. So let me just start, because I'm going to be out of time, by giving a definition. So if you have some function and you evaluate it at, say, one point and subtract the value at some other, that's called the change in f over that interval a, b. Or sometimes we might call it the net change. Or sometimes we might even call it just delta f. Oh, and I see it's time. Okay, yeah, I was just about to start talking about velocity, speed, and displacement, but that's where I'll have to pick up on Friday. Cool, okay. So that's it. I'll see you all on Friday, and I'll hang out to answer questions.